This is section 1.5 in our textbook, linear dependence and linear independence. If V is a vector space with an infinite field, then there are no finite subspaces other than the subspace, which is the trivial subspace, consisting of the zero vector. And to see why, well, if W has a non-zero vector in it, then it has AW for all A in the field. So all subspaces of an infinite vector space are also infinite. And it's our challenge to find the smallest finite set of vectors that will generate or span that subspace. So suppose that S is a set of vectors in W, and that the span of S is W. Our question is it the smallest it could be, or are there vectors that we could omit from S and still keep a span of W? Well, if there are vectors in S, V1 through Vn, and scalars, not all of which are zero, and we can express the zero vector as a linear combination of those vectors from S, then in that case, any one of the vectors with non-zero coefficient could be written as a linear combination of the others. Just move it to the other side and you have a linear combination. And we could remove that vector from the set S and obtain a smaller spanning set for W. For example, in R2, the plane, if we set up this equation here involving three vectors, A1 and constants A1, A2, A3, we can find infinitely many non-zero coefficients that would satisfy this equation. One of which would be A1 is equal to -2, and A2 is equal to 4, and A3 could be -2. So filling in the coefficients A1, A2, A3, you have then this sum here of three vectors that gives you the zero vector. And notice that we can take one of those vectors and solve for it in terms of the other two. That's all this is saying above. If there is such a non-trivial representation of the zero vector in S, we say that S is linearly dependent. We also say that the vectors in S are linearly dependent, meaning you can get a non-trivial linear combination of those vectors that will give you the zero vector. If there is not a non-trivial solution, in other words, if whenever you choose a set of vectors, a finite set of vectors in S, and you write this linear combination here, AV1 plus A2V2 plus A3V3, etc., and set it equal to the zero vector, there is no non-trivial solution. In other words, it implies that all of the coefficients are zero. That certainly is a solution, but it's called the trivial solution. In this case, we say that S is a linearly independent subset of V. We say that those vectors are linearly independent, and we say that the set S is linearly independent. For example, in R2, the plane, if we set up this equation, taking the two vectors 1, 0 and 0, 1, you know that this equation has only solution A1 equals A2 equals 0. So these two vectors are linearly independent. Another example, in the set of polynomials of degree less than or equal to 3, P3 of R, the vectors, I'll put them in braces here, the vectors x cubed, x squared, x, and 1. That is a linearly independent set. Or we could say that those 4 vectors are linearly independent, meaning that if we set up an equation, a1 times x cubed plus a2 times this vector plus a3x plus a4 times 1, and set it equal to 0, the only solution is the trivial solution. a1 equals a2 is a3 is a4, and they all have to be 0. In this first example, we ask whether these 3 vectors from R3 are linearly dependent or linearly independent. So to find the answer to that, we set up the following equation. We ask if we can write a linear combination of these 3 vectors and get the 0 vector. So now see how this results in the following system of equations. Multiplying these out, we get 3 equations in A, B, and C. Notice the first equation, I'm just multiplying to the first coordinate of each of the 3 vectors. 1A plus 2B minus C is equal to 0. Then the second equation, I have minus 1A plus 0B plus 2C is equal to 0, and so on. We get 3 equations in 3 unknowns. Now we could just solve these using algebra, but I'm going to put them into a matrix and do it that way. But keep in mind, we're really just dealing with these 3 equations. If I want to add one equation to another, I could do it. I could multiply an equation by a constant and then add the left-hand sides and the right-hand sides. That would be okay. We would keep the same solution set. I could multiply both sides of an equation by any constant, and I could change position of the equations. If I wanted to put the one on the bottom on the top, that would be okay. So that leads to the 3 different kinds of row operations we can do on the following matrix. I set up the matrix here of the coefficients. That way I just don't have to look at the A, B, and C. Now I need a 1 in the upper left-hand corner, and I have it. So I want to get zeros in the first column other than that 1. So I will add the top row to the second row. That will give me a 0. And then I will multiply it by -2 and add it to the third row. Notice when I did that, I left the top row alone. It's the same. But I multiplied it by -2 and added it to the bottom row, getting this, and then I just added it to the second row, getting the new second row. So now I need a 1 in the 2-2 position here in the matrix. I need this to be a 1 right there. So I'm going to just simply divide through by 2, getting a new matrix. So I just multiplied the second row by 1/2, or divided it by 2, there, and I get a new second row. Now I have a 1 in the 2-2 position, and I'm going to use that second row to get zeros here and here. And I will do that by multiplying this second row by -2 and adding it to the top row, leaving the second row the same, and then I'll multiply it by +3 and add it to the third row. So doing that, I get now this matrix here. And at this point, I would stop, because this really gives me 3 equations with exactly the same solution set as the original 3 that I just erased. This tells me that A minus 2C is equal to 0, that B plus 1/2 C is equal to 0, and that 5/2 C is equal to 0. Well, then C is equal to 0. And if C is equal to 0, then, of course, these go, and we have A is equal to 0 and B is equal to 0. Therefore, this original equation that we wrote is only true when A, B, and C are 0, and therefore we can say that these three vectors from R3 are linearly independent. Now we have 4 polynomials in the vector space of polynomials of degree 4 or less, and we're asking them if they are linearly dependent or independent. Well, you won't have to do this after the first time, but let's think of it as we did the last example. This will be the equation that we want to solve. A times x to the 4th minus x cubed plus 5x squared minus 8x plus 6 plus b times the second polynomial minus x to the 4th plus x cubed minus 5x squared plus 5x minus 3 plus c times the third polynomial x to the 4th plus 3x squared minus 3x plus 5 plus d times the fourth polynomial 2x to the 4th plus x cubed plus 4x squared plus 8x, and we want to know what are A, B, C, and D if they give us the 0 polynomial. In other words, 0x to the 4th, 0x cubed, 0x squared, plus 0x. I want you to be able to see once how you get a system of equations that will solve. So I'm going to expand this all out and collect coefficients on x to the 4th, x cubed, x squared, x, and 1. So you don't need to write all this down, but just look what I did. I multiplied everything out and collected the coefficients on x to the 4th. Notice, let's just look at that one. I have a times x to the 4th minus b times x to the 4th plus c times x to the 4th plus 2d times x to the 4th. And that's what I have collected here. I just factored out x to the 4th. And I did that on each power of x, and we want the sum of all this to be equal to 0. In other words, the coefficient of x to the 4th has to be 0, and the coefficient of x cubed has to be 0, etc. So now I'll write the system of equations, and then we'll just turn it into its matrix form, and you will see something that you can do next time to skip all of this work in blue. So this is the matrix of coefficients of the equations that I just set up. Look back at them for a minute. We know that we want this to be equal to 0, the coefficient of x cubed to be equal to 0, the coefficient of x squared to be equal to 0, and so on. And if you look at this here, if I just take the a's, b's, and c's out, I have 1, minus 1, 1, 2, and I want that to be 0. Notice that is the top row in this matrix. 1, minus 1, 1, 2. So I've just taken the a's, b's, and c's out, and I have the matrix of the coefficients of a, b, c, and d here. What I'd like you to see, though, before we go ahead and solve this system of equations is, and we'll get to this in chapter 2, but look back at the vectors. We had this vector here was our first one, this polynomial. Notice the coefficients of x to the fourth, x cubed, x squared, x, and 1 are 1 minus 1, 5, 8, 6. And look ahead at the matrix. Here, right here, you see that we have taken that first vector and just dropped it in as a column. So, in other words, these are the coefficients here of x to the fourth, x cubed, x squared, x, and the constants. So we wanted to know if the four polynomials were linearly independent. You don't really have to expand it out and write the system of equation in A, B, C, and D. You can just take the individual vectors and drop them in as columns, and you get the same thing. But we will talk about that in Chapter 2. Right now, you can just think of this as the system of equations in A, B, C, and D with the variables removed. So now we want to solve this equation, and I'll do it quickly. In other words, I'll turn this off while I solve it and then let you see each step. The first thing I need is a 1 in the upper left-hand corner, and I see that I have it. So I'm going to add it to the second row, turning the negative 1 to a 0. I'll multiply it by negative 5 and add it to this third row. So doing those row operations, I get zeros in the first column, except for that top row that we used and left the same. Now, looking at this, you can see that the third row is simply negative 2 times the second row. So those two equations are essentially exactly the same, and I can just take one of them out. So I'm going to take out that, and this matrix has one less row. Now I need a 1 in this position here, and I have a 0. So I'm going to take one row and move it up. And I think I will just take this row here and move it up to that second position, move everything else down, and while I'm at it, I'm going to divide by minus 3 to get the 1 in the place that I want it. Alright, so now I have a 1 in the position where I need it, right here, and I will multiply that row. Well, I'll just add it to the top row, and that will give me 0 right there. I have a 0 in the third where I want it, and in the fourth row I need a 0 where the 3 is, so I'm going to multiply that equation, the second one, by minus 3 and add. And this one was just adding. So carrying out those row operations, we get this matrix here. And look, if I multiply the third row by 4, I get the fourth row. So those are exactly the same equations, and I don't need two of them. So I'm going to eliminate the fourth row and continue by getting zeros in this position and this position. So to do that, I will want to multiply the third row. Notice I have a 1 right where I want it. So I can see easily what to do. I'll multiply it by 5/3 and add. And up here, I'll multiply it by 2/3 and add. So now at this point, I have 4 variables and 3 equations. And so let's see what we have here. We have A is equal to 4D. This tells me that B is equal to 3D, and that C is equal to minus 3D, and D could be anything. So why don't we just you say D is free to be any number you give it, let's let it be 1. So in that case, A is equal to 4, B is equal to 3, C is negative 3, and D is 1. This tells us that there is a solution to that original equation and that the polynomial vectors are linearly dependent. If you go back to this spot right here where we wrote out, here let me circle that in red, where we wrote out our original equation, testing for linear dependence or independence. We said, do there exist non-zero coefficients A, B, C, and D? And the answer is yes. And if you plug in A equals 4 here, and B is equal to 3, and C is equal to minus 3, and D is equal to 1, you will see that you do get 0. Theorem 1.6, let V be a vector space and S1 be a subset of S2, a subset of V. If S1 is linearly dependent, then S2 is linearly dependent. Well, since S1 is linearly dependent, this implies that there exists a finite number of vectors, V sub I goes from 1 to n, such that there are scalars A1 through an, not all 0, such that A1 V1 plus A2 V2 plus dot 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 plus A sub n V sub n is equal to the 0 vector I equals 1, 2 up to n, and not all A sub I equals 0. So A sub I is not equal to 0 for some i's. Well, all of these, since S1 is contained in S2, this linear dependent set of vectors is also in S2. Therefore, S2 is linearly dependent. Remember, to be linearly dependent for a set to be, all you need is some finite number of vectors where you can get a non-trivial representation, a linear combination equal to the 0 vector. Likewise, if S2 is linearly independent, then S1 is linearly independent. So in S2, for any finite subset of vectors v1 through vn, a linear combination of them equal to the 0 vector is trivial. A1 through an must be 0. Well, then certainly if we pick any subset of vectors in S1, if we change this to S1 here, this is also a set of vectors in S2. So if we pick these vectors in S1, the linear combination equal to 0 has only the trivial solution because those vectors are also in S. The last thing that we'll do in this video is prove Theorem 1.7. Let S be a linearly independent subset of a vector space V, and let V be a vector that is not in S. Then the set S union V, the set containing V, is linearly dependent if and only if V is in the span of S. So what we're asking is in here is, when we add a vector into a linearly independent subset, how can we tell if the set remains linearly independent? So first, let's suppose that S union, the set containing V, is linearly dependent. Then there exist V sub I, vectors V sub I, in this set S union, the set containing V, such that a finite number of them, let's say n of them, such that there exist scalars a1 through an and a1 v1 plus a2 v2 plus up to a n v n equals 0, and not all of the a sub i's are equal to 0. Not all. Some of them are not 0. Well, we know that S is linearly independent. So that tells us that one of these vectors has to be V. They cannot all be from S. So one of the vectors V sub I, one of the V sub I with non-zero coefficient must be the vector V. So I'm going to write WLOG without lack of generality. Suppose V1 is equal to V. And A1 then we know is not 0. Well, that means then that A1V, which is A1V1 up here, is equal to minus A2V2 minus A3V3 minus dot 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 minus A sub n V sub n. And we can solve for V. A1 is not 0, so I can divide by it. Minus A2 over A1 V2 minus A3 over over A1 V3 minus dot 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 minus A sub n divided by A1 V sub n. We have just written V as a linear combination of vectors in S. So V then, we can conclude, therefore, V is in the span of S. And that's what we wanted to prove. Now we need to prove in the other direction. We need to prove that if V is in the span of S, then S union the set containing V is linearly dependent. Okay, so we're assuming that V is in the span of S. So V in the span of S implies that V is equal to B1, let's say U1 vector, plus B2 U2, plus some finite number of them, let's say M, B sub M, U sub M, the vector, where the U sub i's are vectors in S, and the B sub i's are, of course, from the field that's over the vector space, the scalars. Okay, well then that means that B1U1 plus B2U2 plus B sub M U sub M, that's V. Let's subtract V minus V, then that's equal to a 0 vector. And the coefficient of V is -1. So we have a linear combination, a non-trivial, let's say this is a non-trivial representation of the 0 vector. Therefore, S union the vector V is linearly dependent.